read the sets and functions. This is if very basic concepts in mathematics and almost in all streams of engineering and science, we require the knowledge and the concepts of these two. So, first we read the set. We define set. Very simple way, if we define the set is an unordered collection of objects. These objects are normally, sometimes we call the elements or members, called the elements, or sometimes we call they are the members of the set. Another property of set is that unordered collection, that are normally the elements we are considered, these are, or these objects are distinct objects. And as already mentioned in the definition, or unordered, that means in which order it is coming, that is set is, in the definition of set we do not concerned, or set is not defined. So, that is why in the definition itself we mentioned that it is unordered collection of objects. Like we tell the set of even integers, or even before that I can write, normally we write the notation is, say A is defined as the set, say it is 1, 2, 3, 5, 7. So, this is the notation normally we use to define a set. So, here these 1, 2, 3, 5, 7, these are the elements or objects of the set. These are the elements of the set. And like I can tell that X is set of positive integers. Or Y is set of even integers. Similarly, I can define that R is set of real numbers. And if I denote that, or I can, this thing also I can write, say set of positive integers, I can write X is X such that X is a positive integer. So, here both the definition are same. Here if I write x is set of positive integers, same as I also can write, this thing also I can write that x is small x, x is a positive integer. That means, all x which is a positive or x which is a positive integer, that must be one element of this set. Normally, we denote that the x belongs to x. This is the notation we use, that x belongs to the set x. So, normally this is the notation we use the small letter to denote the element of a set and the capital letter which denotes the set itself. So, normally we write that x belongs to x. Here x is the element and capital X is the set. Now, just now I gave example that one set A which has only say 5 elements 1, 2, 3, 4, 5, 7 say 6 elements. Okay. There are 6 elements or there can be 60 elements, and I can take that x such that x is a positive even integer. So, here the number of elements, how many elements are there? Only 6. So, if the set contains finite number of elements, then it is a finite set. So, in this example A is a finite set, since it contains only 6 elements. But say B we have defined B contains all the positive even integers, and how many positive even integer we have? This is infinite number of positive even integer 2, 4, 6, 8, just we 100, 102, 104, there can be infinite. So, there is something called infinite set. That means, if infinite number of elements are there in the set, it is an infinite set. So, the how many elements are there in the set, that actually gives the what type of set it is. So, number of elements is a important thing in the set, and we define that is as the cardinality of the set. Normally, we denote, so the cardinality of the set gives the number of elements in the set. We define or we denote that as the cardinality is in this way. So, this gives the cardinality of the set, that means the number of elements. is the cardinality of x. So, previous example, this is equal to 7 for finite set A. Now, there can be some set that where no element is there, that means I have a set where there is no element. So, normally this is called a empty set or null set or void, we just tell null or void. So, this is defined as set having a set with no element. It has another notation, we used this as the null set. Okay. Now, when can we set or when can we say the two sets are equal? Say let we have two sets say x and y. So, we can tell x equal to y. So, we can tell x equal to y. So, if for all x x belongs to x implies x belongs to y, and x belongs to y implies x belongs to x. Then two sets are equal. So, what the meaning? That means all elements of set x and all elements of set y are same, then the two sets are equal, and that in propositional logic, using propositional logic we can write x equal to y if for all x, x belongs to x implies x belongs to y, and x belongs to y is x belongs to x. That we know that x is a set, for x set x, for all we can write that for all x, x belongs to x, that means small x are the all elements of x. Similarly, if we consider y, then for all x, x belongs to y. Then the proposition that if we get that for all x, x belongs to x implies x belongs to y. That means, for all elements of x, again they are the elements of y, and similarly all elements of y implies that x, this implies they are all elements of x. Then if this is true, then I can tell then two sets are equal. So, this is the way to show that two sets are equal. When we have to prove, to show or to prove, then we have to show this this propositional logic to be true. Now, we take one example. Okay. We take one example. Say, prove that if a equal to x such that x square plus 2x minus 8 equal to 0 and b equal to, say I have two elements minus 4 and 2, that they are equal, then the two sets are equal. So, first x belongs to A implies I have to show that for all x, what do I have to show? For all x, x belongs to A implies x belongs to B. So, what type of set A is? A is x such that x square plus 2x minus 8 equal to 0. So, if I put what x square plus 2x minus 8 equal to 0. So, what value of x this equation is true? So, if I solve x square plus 4x minus 2x minus 8 so, this is x plus 4 x minus 2 equal to 0. So, x equal to minus 4 or x equal to 2. So, x belongs to A, that means for minus 4 or 2, that if x belongs to A, that means x equal to minus 4 or 2. So, this implies that if x belongs to A, that means for all x that satisfy. So, for this case, this is actually our case 1, that for all x, the x, if x satisfies the equation x square plus 2x minus 8 equal to 0, then the value of x are x equal to minus 4 and x equal to 2. What we see that B is the set of elements minus 4 and 2. So, x belongs to, so x belongs to B. So, our now what is our case 2? Our case 2 is for all x, x belongs to B implies x belongs to A. Now, we see x belongs to B, x is minus 4. So, if x equal to minus 4, then x square plus 2x minus 8 equal to 0, it is true. If x equal to 2, then x square minus plus 2x minus 8 equal to 0, true. That means, for x equal to minus 4 and 2, a x, that x square plus 2x minus 8 equal to 0, this is true. That means it is x belongs to A. So, what we see that both the cases, that for if x belongs to A, then it implies x belongs to B, and x belongs to B, it implies x belongs to A. So, we prove that A equal to B, since we have proved that for all x, x belongs to A implies x belongs to B, and x belongs to B implies x belongs to A. So, this is the way we should show that if two sets are equal. Now, we define the subset of a set. We define subset. Suppose x and y, x and y are two sets. If every element of x is an element of y, we say that x is a subset of y. And we denote that x is a subset of y. So, this is my notation of subset. So, we take example is very simple example we can take, say my x is 1 and 5 and y is a set, say 1, 4, 5, 7, 9, like that. So, what we see that every element 1 belongs to y, 5 belongs to y. So, I can take that x is a subset of y, since 1 belongs to y, 5 is also belongs to y, and my x is 1 and 5 only. So, this is my subset notation. We see the example, another example we see that prove A is a subset of B where A equal to x such that x square plus x minus 6 equal to 0 and B is the set of integers. B is set of integers. So, A is all such x that satisfies this equation, and we know that x square plus x minus 6 equal to 0. That means, for x values are x plus 3 into x minus 2 equal to 0. So, x equal to minus 3 and 2, and B the set of all integers. So, minus 3 is also belongs to B, 2 belongs to B, A is actually the set of minus 3 2, because that satisfies this. So, my A is the subset of B, proved. A is the subset of B. Now, x belongs to, if that using the propositional logic, if we write that x belongs to A implies x belongs to B. Now, if for all x, for all x it is true, if it is true for all x, then we tell that this is A belongs to A is the subset of B. So, for all x, whether this is true. Now, if I write using our logic, for all x, x belongs to A implies x belongs to B, okay, and this must be true. Now, say this is one proposition or basic statement, I think that P, and x belongs to B, another statement Q. So, if it is for all x, P implies Q, if I think that is true, where P I have assumed that x belongs to A and Q I have assumed that x belongs to B. Okay. Now, for all x, I have to show that this is true for all x. Now, if it is to be false, if my statement, this conditional statement, because this is a conditional statement. So, if this implication or conditional statement is false, that means negation of this is true, that is negation for all x, P implies Q this is true, that means negation, if this is false then this should be true. If this implication is false. So, that means we remember that negation, if P implies Q, okay, if we remember the formula that P implies Q is equivalent to negation P or Q. So, if I take negation of P implies Q, which is equivalent to, we apply De Morgan's law, Q is equivalent to P and negation Q. So, if we apply here this thing, that means this is negation for all x, my P is x belongs to A and implies, sorry, x belongs to A implies x belongs to B. So, negation of for all x means there exists x, negation of x belongs to A implies x belongs to B. So, this is simply P Q. So, negation P Q, what we have seen, negation P implies Q is P and negation Q. So, this becomes there exists x belongs to A, P and, so and negation Q, that means I can write negation Q is does not belongs to B. That means here negation Q is x does not belongs to B. So, what we get, and that must be true, it is true, this is true. So, what we get? So, if it is a subset, A is a subset of B, then we tell that A is a subset of B, that means x belongs to A implies x belongs to B. Now, if it is false, then the negation is true and we get there exists x, that means there exists at least one x, for which x belongs to A, but x does not belongs to B. So, if we have to show that A is not a subset of B, that means what? We see that if we want to show that x is or A is not a subset of B, where A, B and 2 sets, then I have to, then at least one element, then we have to show that there exist at least one element, say x, that which belongs to A, but does not belongs to B, then it is not a, then A is not a subset of B, then A is not a subset of B, A is not a subset of B. And but if I have to show that A is a subset of B, then for all x we have to show for all x, this is for all x, this is true for all x, and here this is at least, that x, this implies x belongs to B. So, the summary is that if we have to show that A is a subset of B, then I have to show for all, this is the thing, the for all, and if it is not, then at least like the counter example, we have to show that at least one such x exists that which belongs to A, but does not belongs to B. Now, with this concept we can use the set union, we can define set union that A and B are two sets, then the union of A and B contains elements which are either in A, that means elements belongs to A, or B, or in B, or both. We normally define that or denote the notation that A union B that is, but we do not, these are the notation that A union B. That means, we tell that x belongs to A, x belongs to A, or x belongs to B. Now, A intersection B, that we write x belongs to A and x belongs to B. So, intersection is all the elements so set intersection that for sets A and B, A intersection B contains elements that belongs to both A and B. And what we write that A intersection B is equivalent to, we write x belongs to A and x belongs to B. And set difference if A and B are two sets, then A minus B, we can write that x belongs to A and x does not belongs to B. Similarly, B minus A, that x belongs to B and x does not belongs to A. So, these are my set operations. We define union, normally denoted by A union B, intersection is set difference is A minus B or B minus A. Normally, these are the operations we use on the set. There are many other properties on set and that we will discuss in the next class.